now that I've thoroughly confused you about what voltage is, and I again encourage you to think your way through it. You don't need to know all that exact math, just a basic idea that it's a trick in what it is, that it's your potential to move a charge. Let's start looking at some equations we can use to then calculate this, because the idea is we started with forces, we had Coulomb forces, and then every time we changed anything we had to redo that whole problem, and it was a vector. So we used the math trick to get the electric force, which simplified it. We could do most of the work ahead of time and then just plug in a charge to get the force, but it was still a vector and it was a pain. But then we found that there was a property about this vector that let us represent it with a scalar field. We called it voltage, and now this is where we are. Voltage is a scalar, it's not a vector. Scalars are really easy to work with. So if I had a group of charges, a positive charge, and a positive charge over here, and I wanted to know the total force acting on this thing, and we could say I had a bunch more of these. I could either go through and do Coulomb force on all of it, or do the electric field because of each of these charges. This would make an electric field that way. This makes an electric field that way, and one pointed towards this one that was supposed to be pointed toward it. So pretend it's pointed, right over there toward it. And I'd have all these electric fields, e to the positive, e to this negative, e to this negative over here. And I'd have to add all these up, and it's adding up vectors, and it gets crazy, still complicated, especially as I add more and more charges. So what we want to do is go to this voltage, and the idea is that I can go through and instead of calculating all these electric fields at this position, I can just calculate a voltage due to that positive, and then I can just add on a voltage due to this negative, and another voltage due to this other negative, and I can just add these scalars up and get the voltage at that point. And it's a lot easier to just add scalars than it is to do the vector sum of 3 or 4 or more, or a whole bunch of vectors, because as we get more and more, this gets a lot easier, and you don't have to worry about angles or anything like that. It's very simple to just add them up, and I'll probably make a video doing some example problems in this section, because I think it's pretty beneficial to see some sample problems on using these. So let's go ahead and start with our first equation we had, that was V equals our potential energy per unit charge. I'm going to go ahead and put this delta in front of it, because you really never have just potential energy. It's technically should always have that delta in front of it. So I'm going to go ahead and put that there. And this is our first equation right there. It's your potential energy per charge, and that's pretty much it from there. So now let's look at, well, how do we get this electric potential energy? So let's go for our second equation here. We're going to go through these pretty quick. They're not really difficult to derive. Well, we know that work is equal to a change in potential energy, if you remember that from before. And like if I lift something up in the air, the work I did against that field is how much potential energy I gave it. And we know that work is force times displacement. All right, so let's work with this force times displacement. Well, what's electric force? It's the Coulomb force. So in this case, that would be Coulomb force. Well, Coulomb force is just Q times E, and then it's times the distance you move through this. So if we have a constant electric field, right, we can just do Q times E. That's how this one works for constant force. So a constant electric field, so this is with a constant E field, right? It's uniform, it's constant everywhere. We can then just say the change in potential energy is Q times E times D. All right? And so what I mean by that is you'd have some electric field like this. Here's some electric field, uniform. All my lines are staying the same distance apart here. So remember, the strength of electric field is the distance between the lines. These lines are all staying the same distance apart, which means uniform or constant electric field. I can have some charge that I put in here, some charge, I won't say if it's negative or positive, and then I can move it along through here and have some sort of change in potential energy there. Okay, and that equation there would calculate it for us. So before we get too into that, I'm going to put a point here. I'm going to call this point A, and this point B, and then I'm going to put a point C here right directly above point B. And let's talk about a few things here. First, there is something else we've got to add on to this. It's just by convention, but we're going to add a negative sign here. And the reason for the negative sign is really just to give preferential treatment to positive charges here, so that when positive charges move in the direction of the electric field, they have a positive or they have a decline in potential energy, because that's the way they want to go. But then it works out to be the opposite way for negative charges. So it's just there to give like this preferential kind of treatment and make everything work out. And you'll see what I mean. It just makes it gives it that way, so that if you move the direction you want to go, it gives you the right idea that it lost potential energy instead of gained, even though we can kind of define it however we want. But it's a convention that's put there for. Just remember it's there. Okay, so if I take a positive charge and I move it from A to B, is that an increase or decrease in potential energy? Well, think back to gravitational potential energy. Let's say this is the ground here, and we have an object. If we take that object from here and move it up, we move this in the opposite direction that it wants to go, that's an increase in potential energy. So moving it up, again, in the opposite direction it would want to go on its own, that's a change in potential energy, that's an increase in it. That's an arrow up. If we take an object and we lower it the direction it wants to go, that's a decrease in potential energy. That's a down. Okay? If it goes the direction it wants to go, potential energy decreases. If it goes the direction it doesn't want to go, you make it do something it doesn't want to do, that's an increase in potential energy. So I have a positive charge at A and I move it to B. So the question is that the way that a positive charge would want to go? And the answer is yes. Positive charges follow in the direction of the electric field. If you think of it, electric fields point at a positive, so that means we must have some kind of positive charge over here, and they go into negative, and or we must have some kind of negative charge over here. Really, to get this uniform charge, you have like a bunch of positive charges like in a line or something like this, and a bunch of negative charges in a line, and it makes that negative electric field. But we don't need to think about that at the moment. We just need to know they're going out of positive into negative, and positive charges follow in the direction of electric fields. So a positive charge moving from A to B is the direction it wants to go, and that is therefore a decrease in potential energy. So look at the equation. We have a negative times a positive charge here. All right, that's a negative. And then look at this. The electric field and the displacement there, they both have a direction. Our displacement in this case is in the same direction as the electric field. So if the electric field is positive, the displacement, D, is positive, and we have a positive times a positive, that becomes positive. We have a negative of our positive charge, so we overall have a negative sign there. It's a negative, positive, positive, positive. Now, what if it was a negative charge we were moving from A to B? Well, for the negative charge, we have a negative of the negative charge, so it becomes positive. And then we have the electric field and the displacement are both positives, and so it's positive. It's a negative, negative, positive, positive. That's a positive. And that's an increase in potential energy. And if you think about it, if we had a negative charge here and we let it go, it would want to go to the left. It would want to go in this direction over here. But if we're forcing it go to the right in the direction of the electric field, that's the way it doesn't want to go. Negative charges want to go against electric fields. We're making it do what it doesn't want to do. We should have an increase in potential energy, and the equation gives it, thanks to that conventional negative sign that we put there. And again, it gives that preference to positive charges because we just chose that that's the direction of the electric field. The electric fields could have been chosen in the opposite direction, in which case we wouldn't have that. So anyway, it's just a convention to go with the preference of positive charges, even though there's no real reason for the preference of positive charges, it's just the way it is. Okay. Now, what if we went the other way? What if we turned this displacement around and we had them displace in the other direction? Well, for a positive charge, that is against the direction it wants to go, so we should get an increase in potential. So what will we have? Negative of a positive, it's a positive charge, a positive electric field, and a negative displacement. That's a negative, a positive, and a negative. So that's two negatives, that's a positive, that's an increase in potential energy. For the electron, we have going in the direction it wants to go. It wants to go against the field, so that should be a decrease in potential energy. That's a negative of a negative charge, of a positive, of a negative. So it's three negatives, that makes a negative, it's a decrease. Okay? The last little thing I want to think about this is what happens if we move from B to C? Well, B to C, we're moving perpendicular to the electric field. And If we move perpendicular to the electric field, we'll come up with a name for it later. I'm not going to do it right now. We are essentially not having a displacement in the direction of the electric field. These two have to be parallel to each other because if you remember, for work it was force parallel to displacement. So these are perpendicular. It has to be electric field perpendicular to displacement, really. It has to be electric field parallel to displacement. We're not actually changing in electric field strength in any way. So moving any charge from B to C or C to B is actually going to be no change in potential energy. It's like moving something parallel to the ground. It's no change in potential energy. It doesn't care if it's here or here. It has no preference. So no work is done, no change in potential energy moving perpendicular to electric fields. And the same thing will hold true if our electric field is like the electric field coming out of a positive charge, if it's pointed outward like that. We can move perpendicular to these electric fields, but of course staying perpendicular to these electric fields means we have to actually go in a circle. And that would essentially be orbit, and no work would be done as we moved around that circle. Okay? And again, we'll come up with a name for these lines later on. So let's go to our next equation. We're going to start combining these two. So let's take this one, and let's combine them off over here. So what do we have? We have voltage equals change in potential energy over Q, but this is then negative Q ED, that's potential energy, over Q. And so the Q's will cancel, and we'll be left with V equals ED. Okay? Well, actually, negative ED. And there's our next equation for that. What this will tell us is not the change in potential energy, but technically the change in electric potential. So if we weren't moving a charge and we were just looking at the electric potential between these two places, this is what you would do. Very similar to what we did here. Again, this negative gives that preference to the positive charge. So if I go in the direction of the electric field from like A to B, that's a positive electric field, positive displacement. They're in the same direction, so even if they're both negative, if it's a negative electric field and a negative displacement, if they're in the same direction, they're going to multiply together to give a positive number, and then we have a negative of a positive number. So voltage decreases like potential energy does for positive charges. So that's what I'm saying, that negative gives that preference to those positive charges. It makes voltage change in the same direction that potential energy does for positive charges, but then voltage changes in the opposite direction for how negative charges do. So be sure to kind of keep that in mind. Okay, and that leaves us down to then one last equation we can then take here and derive from this guy. I'm going to replace D with R, just because this is distance, this is distance and R is also distance. So if we have V equals negative E R, well, we know what electric field is. Electric field is KQ over R squared, but now we're multiplying it by R. Okay, I'm ignoring that little negative sign for a moment. Technically it should still be there, but I'm just going to ignore it for the moment. And so we have R squared, R times 1 over R squared gives us that, and we'll get that V equals KQ over R. All right, and then that'll be our last little equation for this. And this is electric potential due to a point charge. So this would be like that example where I talked about up here, where we wanted to compare what these potentials are. This would be this right here. You would do K, Q, the positive charge over R, whatever that R1 is, plus K, Q of that negative over R2, whatever this is. This would be R1, this would be R2, this could be R3, then it'd be plus K, whatever this should probably be, 2 negative, 3 negative over R3, and you just keep adding them up, and you get the voltage due to each of these point charges from this equation here. So again, this is for a uniform field. This is the voltage due to a uniform electric field. This is the potential energy due to a uniform electric field. This is like our definition of voltage, and this is the voltage you get from a single electric charge, and it's essentially this you can relate back to potential energy. As you can imagine, it's the amount of work it takes, like almost to build that charge, to bring that charge in from infinity and put it in a place. So if I took this and multiplied it by the charge, right, from this we get that potential energy is equal to QV. So if I calculated the potential energy of a charge, multiply it by V, it would basically tell me how much energy it would have taken for me to, if we look back up this picture, to have taken, we have this charge here, for me to take and like put that charge there. If that makes any sense to you, but it's the amount of work it takes to like almost build an arrangement of charges. Okay? I think that's pretty much it for the equations here. I'll try and make a video at least showing you how to use each of these equations, and then that'll be that.